8% interest for 10 years. So let's see how different compounding periods affect the growth of your investment. Okay, so you put it in for a straight annual, and you're going to have, after 10 years, $2,590.71. Okay. You have the money compounded quarterly, so that 8% is being divided 4 times. So it is the number of times that it is being compounded over the 10 years. I'm going to give you a formula for this in a few minutes. This one was monthly, so it's at 8% divided 12 times. So it's happening 12 times over each of the 10 years, or how much? 120 times it's going to be compounded. Okay, daily, this is each hour, and this would be by the minute. So let's look at the totals after 10 years. Okay, so if you did it just once a year, you're up to $2,600. Here it went up, maybe, about $50. Here it is, what, $13 more. Here you have gone $7 more. Here you've gone up, what, 23 cents more. And here you go up 1 cent. So what happens? The more frequently something is compounded, what happens? It what?
The less the amount gets.
The less the amount gets. Can we use another word for that?
Isn't it the less
The increase?
Because it's actually more money, but it's changing less. So.
It's changing very, very little at this
Constant
point.
difference.
And so we say that we are approaching a limit. Okay, so we are approaching a point that it's not going to increase significantly more. Okay, what?
So is it the bank who would decide how many times a year it would be?
Oh, they all advertise. Go online and you'll find different banks doing different things. Or, I mean, you know, we have lots of different things. Engineers use it. If you study health, populations. Is our population, if you go to Times Square and you look, there's a big clock on the thing, and it is changing constantly as they calculate births, deaths around the world, or in the United States, or whatever. So things are changing, and it appears to be approaching, but you can see the numbers ticking away.
But what about when the power goes out?
I think they have a battery pack or something to keep track. Not now. So, all right. Okay, so here is a formula that I'm going to ask you to copy down.
What can we label this?
This is going to be number E. We're going to be talking about E. E. It is the number E.
Number E, I like that.
Is I a number?
Is I a number?
Of
Yeah, we
course.
call it a number.
Represents a number.
Yeah.
It's not-
Okay. Okay, so what people discovered was, and in this particular problem, what they did was they did a test, and I don't remember the name of the guy, and he's mathematicians, Euler, I believe, is one of them. Okay, and I'll just give you another little bit of historical data. The number E, this guy Euler is a big mathematician. He's done a lot of studies and in a lot of notation. So remember that symbol that we see on the board I showed you for the calculus? Leibniz and Euler are responsible for a lot of that notation. And this guy Euler was responsible for this notation. And people suggested at one point that he named it after himself because his name is E. But the other theory is he was, and I thought that this was kind of funny, he was already using E as the next vowel after A, and he was already using A in his notation, and so he decided just to use E. And the first time that it appeared was in 1731. So, and he was writing to his buddy in another part of Germany, and we're going to talk about what E represents, actually. Okay, so in this particular scenario, all we're doing is we're trying a problem. Let the original number P equal 1. I'm going to use 1 here. And the yearly rate, I have to zoom out, sorry. The yearly rate is going to equal 1, or 100% for 1 year of growth, compounded k times. So if we plug in all these k's in here, we end up with an approximation that this number is the number, that limit that we approach, and that is what E is. So you can copy that number down. That is, I thought I had it on another piece of paper. E is right here, and this is the approximation. Euler gave this number, hold on, Euler gave this number in to 18 decimal places. What kind of a number is that?
Irrational.
Irrational. Am I asking you to know 18 numbers out?
No.
No. What do you think we will go with?
Round up.
2, 7, 1.
There's an E button on your computer.
Their calculator. Yes. Now I'm going to show you how to do that in a second. Okay? So when something is being compounded continuously, we're going to use a different formula. We're going to actually use, you don't have to write all these down. I thought you'd appreciate being
Do
able
you
to.
know what the R and the N and the K were in that formula?
Okay, I'm going to give you this information in a second, okay? All right, so we are going to use 2 different equations here. Here's your other equation right here.
Where'd it go?
Oh, where did it go? Okay.
Do we need the first?
You're going to use 3 different equations depending on what you have.
Did we need the one from the other page where it's like A equals B
Yes, yes,
equals
yes.
0?
I'm going to give them to you again. So you're going, the value of the original investment of P dollars with an interest rate of R, that's an R there, compounded continuously for T years is equal to P E R T. Okay?
So the second one was continuous, what was the first one?
Well, the first one can also be, the first one is used for 2 different ways, and I'll give you an example. The first one was, you know, this model that I gave you here. So this, and I'm going to write this out for you. Hold on, right here. You need this equation. And this equation, let me see if I can clear that up.
That's
here.
the only part of it though, because that other one
Yes,
has
no,
more.
you didn't need to know the other one. Okay. This one is, if it is going to be compounded for a couple of different times. So it could be a monthly time, or it could be daily or yearly. And that was that chart that I showed you with all the different equations.
Wait, what's the N equal?
So N is going to be, all right, R is your rate, okay? N is the number of times compounded. Okay, so if it was compounded 12 months, it would be the rate over 12. Okay, and then here our T is still what? Time.
What's P?
P is your principal. That was the initial amount. We had discussed that yesterday.
Oh my gosh.
Okay, so, coming back, let's just look at these equations on the top. So in this one, do you see the principal was, here was the principal amount, it's 1 plus this quantity, and if it was over 1 year, it would be divided by 1. Where's my eraser go? If it was quarterly, it's going to be divided by what? 4.
Is K just a constant
compounded the number of times. You don't need to do the K1, let's just stay with the N and the T, okay?
So which one can we have written down?
The two that I'm giving you are A equals principal 1 plus the rate over the number of times, and it's the number of times T, okay? And really, that's the same as, this is what we did yesterday, P times B times to the T, okay? This is the same, only we know that we have to divide the rate by the number of times, and this is the number of times times the number of years. And then this is P, E, R, T. I'm going to give you one problem to do.
It said P-E-N.
P-E-R-T.
Oh, right, I
P-E-R-T. So let's try this. I want to show you on the calculator where this is. Okay, on your calculator. So let's do this problem. Suppose $200 is invested.
That's 2,000.
Supposing 2,000, where am I? Right here. $2,000 is invested
No, what is
in a 3-year certificate of deposit that earns 6% interest, compounded continuously. How much will the investment be worth? It's compounded continuously. So, on your calculator, turn it on. If you look underneath, where am I?
Log.
E is the third button under, or second button under clear. And it's right, like pi is above it, and E is there. So I would use what? Second, my second, and then the divide button will give me E.
Wait, I can't see your calculator.
Okay, it's the divide button, here's the clear button, here's the caret button, and here's the divide button on the calculator. Okay, and E is right above it. Hold on a second, Cassie. So if I had